Hello. Okay, I thought about it and I figured it out. So we've got a proof for this claim. Um, the claim that we were working on is let S be a convex set. Sigma, gamma are loops in this punctured domain, such that their projections have turning number 1. So they go in their projections go in the counterclockwise direction for 1 full turn about x. And the claim is that these are freely homotopic. So we're going to create a free homotopy for them. So the way that we're going to prove that is we're going to say, so we're going to take this simple case where x equals 0. This makes it a lot easier. The general case follows just by translating. So if we're like puncturing on this disk with x, and if we just translate the entire set and the curves sigma and gamma, if we just translate these by x, then we get the 0 case. So if we prove the 0 case, then the rest follows by translation. So the way that we're going to do this is essentially we're building up to a projection of our functions onto a triangle, which has a certain particular property. So take a simple case where x equals 0. The general case follows just by translation. So take, for each z, which is a non-zero complex number, define this sine of function, sgn, as z divided by the absolute value of z. So this is also, you could say this is e to the power of I times the argument, or complex argument of z. So essentially it's just the polar direction. This is a continuous map, which maps the C star to S1. So S1 is the unit circle, and here we're identifying the unit circle as the complex unit circle. Since our projection P1 sigma has turning number 1, this composition, if we take the sine of the projection of sigma, this has to be surjective. So we have to hit every orientation, because we're doing this full loop around 0. So since it's surjective, we can find these points. We'll find P0, P1, and P2. These will be points on the image of sigma, the curve, which satisfy this property that the sine of P sub j is just this. So e to the power of I2 pi j divided by 3. So essentially, we just want to find 3 points, which are, it's fine if they're in our curve sigma, but really what we want is they have to be in S. But we have these 3 points which are on sigma, which is in S, and they have this property where their sine of, actually this should be the sine of the projection, not just sine of P1. Let me go fix that. That is in the end of the first paragraph. This should be sine of P1, P sub 1, first projection. Yes. So the sine of these projections, of the points, it's just, the first one is at angle 0, the second one is at angle 2 pi on 3, which is like to the upper left, and the third one is at angle, the second one is at angle, 2 pi on 3. The third one is at angle, which is actually, the third one is labeled P sub 2. The third one is at angle 4 pi on 3, which is on the lower left of the unit circle. So we have the right of the unit circle, the upper left, and then the lower left. This is useful, so we can define a triangle delta as this function. So it's going to map it's going to be a loop characterized by this concatenation. So we're just considering a triangular loop, just a triangular loop which passes through these points. So from P0 to P1, from P1 to P2, and then from this should be P2 back to P0 again. Let me fix that. P2 to P0, yes. We're gonna, instead of having the domain as 0, 1, the unit interval, we're just going to sort of make it easier on ourselves and just use the circle, the one-dimensional circle, the unit circle. So we're gonna have this triangular loop. It follows these points. Since all of these points, P0, P1, P2, these are points in S, and delta just draws these line segments in S, so this will stay inside the set S by convexity. using this, we're going to define this function rho. This function is the sine of the first projection of delta. So it can be verified that this rho function is a homeomorphism, actually. So this function rho, it maps the unit circle, so the input is the input of delta, which is the unit circle, and the output is the output of the sine function, which is also the unit circle. So it can be verified actually that rho is a homeomorphism. And the way that we do that is essentially to show that a function is a homeomorphism, it has to be a bicontinuous bijection. So it has to be a continuous function, has to be a bijection, and its inverse function has to be continuous. One of the ways to do that is to show that, well, first of all, we show that it's a continuous bijection. So delta, p1, and sine, these are all continuous functions. Delta is a bijection. P1 is not a bijection, but it is a bijection on the image of delta. And the sine function is also a bijection on the image, or an injection on the image of the composition P1 composed delta. And then we just verify each one of these are open maps. I just sort of left that out because it didn't seem useful. But by verifying that this function rho, this is a open map, we can then say that given that this rho function is a homeomorphism, that means it has a continuous inverse function. So we're going to define this function here. This is phi sub sigma. And so this function has kind of this really complicated design. But essentially we take the input point t, which is in 0, 1. We apply sigma, then we take the first projection, then we take the sine, and then we take rho inverse, and then apply delta. This is really complicated, but essentially what we're doing is we're taking a point on sigma and finding a point on delta which has the exact same sign as on the first projection. And the way that you verify that is if you just take the sine of p1 of phi sigma, this will be the sine of p1 of delta, which is the rho function, and then of rho inverse of the rest. So the rho and rho inverse cancel out, and you just have the sine of p1 of sigma, which is right here. So it's essentially we take our input point t, and we find the point on delta such that sigma of t and delta t, sigma of t and that point on delta have the exact same sign on the first projection. This is really useful. So because we have this last function in this composition is delta, phi sub sigma is a subset of delta. It always maps onto delta. It's also a subset of S, since delta is a subset of S. And it has this property, so this signs. It essentially projects sigma onto the curve delta. Using this phi sub sigma function, we can then define this other, our homotopy essentially, of the first one, of 3, I guess. So we have this function fts, and essentially we're just going to do this convex sum between sigma to phi sub sigma. So we start when s is 0, this will be zeroed out, and we'll just get sigma t. And when s is 1, this sigma t will cancel out with this one, and we'll just get phi sub sigma t. This function f, so phi sub sigma is continuous, sigma is continuous. This is a convex sum of things that are in S. So f is continuous, and it stays in S. And we can also verify, since both sigma and phi sub sigma have the same sign on their first projection, it actually happens that, let me fix that right there. Since sigma and phi sub sigma have the same sign on their first projection, and we have this convex sum between them, then the convex sum itself also has that same sign, has the exact same angle, basically. So f, this function f, has, regardless for any fixed t, it has the same sign, regardless of S, it has the same sign as the sigma curve does. And since this is true, it always has the same sign. We have to have F as being a subset of this punctured disk, S punctured through 0. So F is never 0 on the first index. Using that, F is now a free homotopy. So we start with sigma, we end with phi sigma. It's continuous. It stays in this punctured S punctured through 0. So sigma is now freely homotopic to phi sub sigma in S0 S compose 0. And so we just have to finish this out here real quick. So the conclusion to this is we'll repeat the same process. So we've done this process with the curve sigma, but we can actually repeat this. So we can actually repeat, we just want to repeat this part. So we'll say, so we'll repeat a similar process for the curve gamma. So, so now, hold on. Now we have var phi gamma and var phi also sigma as being subset to delta, and such that var phi sigma, actually we can say, yeah, the projections P1 var phi sigma and P1 var phi gamma still have turning number 1. Since delta is homeomorphic to the circle S1 via actually itself, delta is a homeomorphism from the circle S1. It follows we can apply delta inverse compose P1, actually just var phi, and delta inverse compose var phi of gamma So repeat a similar process for gamma. We have this and this subset to delta. These projections still have turning number 1. Delta is a homeomorphism for the circle S1. We can apply, actually we can say yeah, actually that's fine. So we just apply this delta inverse on these. And then showing that these curves are homotopic. Actually, we can actually just say, by premise, these curves will still have turning number 1. Yeah. Yes, these curves still have turning number 1, and thus are homotopic in S1. And that is pretty much the whole proof. So once we project verify sigma onto delta, we repeat a similar process, just this part. We repeat that part for the curve gamma. So now we have verify sigma, verify gamma as subsets of delta. And of course, sigma is homotopic to verify sigma, and gamma is homotopic to verify gamma. And these projections still have turning number 1. Since delta is homeomorphism from the circle S1, we can apply delta 1 on these curves. Yes. We can apply delta inverse on these curves. And then, and since these curves still have turning number 1, they must be homotopic in S1. And then by composing all the homotopies and homeomorphisms, we see that sigma and gamma are okay, so then we could say yes, okay, there we go. Yes, so we project both curves onto delta, and since delta is homeomorphic, actually the function delta is a homeomorphism from the circle S1. We can apply delta inverse on these. They still have turning number 1, so they must be homotopic in S1. By applying delta again, we see that they are homotopic in the image of delta, and thus in S punctured through 0, since delta is subset to S punctured through 0. Proving that just by composing all the homotopies, sigma and gamma are homotopic as well. And that is the proof. Yes. These are definitely going in an appendix. I don't want them in the middle of the paper. But there they are. Let's pick these up. Yeah. Yes. Yeah, we could probably flesh them out more. So we sort of skip a lot of the work. So for example, we at the very end we just use the fact that these have turning number 1 to just sort of, you know, not have to worry about anything. We just sort of get the homotopy for free. Actually, rather, yes, yeah, we get the homotopy pretty much for free, just by definition of them having turning number 1. One could say that the definition of a curve having turning number 1 is that it is homotopic in the punctured disk to the unit circle S1 in the positive direction. So we sort of get that for free. All of these are, you know, lots of, you know, hoity-toity topological ideas to get this final thing to happen. But essentially we just sort of want the result here, and we don't want to get too much into all these other things. Anyway, so this is this. We're going to have one more result as actually a corollary. So let C1, C2 subset to A be convex, and X be in C1 intersects C2, and suppose sigma subset to C1 punctured through X, and gamma subset to C2 punctured through X are hold on, C1 and C2 be convex, and X is in their intersection, and these two curves are subset. These be convex and X be in this, and these be contours, actually loops, such that P1 of sigma, P1 of gamma have turning number 1 about X, P1 of X. Then sigma gamma are homotopic in the union C1 union C2, punctured through X. Wow. Okay. That's a lot of words. Let me verify that is correct. Okay, so we have two convex sets, C1 and C2. We have a point in, actually we can just say X in C1 and C2 be convex. Okay, so C1 and C2 are convex. And sigma, gamma in these sets are loops with their projections having turning number 1 about this projection P1 of X. Then sigma and gamma are homotopic in this union punctured through X. Okay, so what we're trying to say is that if we have these two different curves have turning number 1 in two different convex sets, actually, let me think about that one. Okay, yeah. Let me phrase that a little differently. Let X be in. Okay, so let have convex neighborhoods. And let sigma gamma be loops such that the projection have turning number 1 about P1x. Then sigma gamma are homotopic in, and instead of this union we can actually just say S. Okay. Or we can no, this is fine, I guess, for now. So the proof for this is actually going to be really quick. So we've already proven that we can contract in the direction of x, are freely homotopic. Let me write that. So we've already proven that we can contract any loop like this. We've also shown that if they're in the same convex set with these turning number, then they're freely homotopic. If they're in the same convex set S. But now we have two different convex sets, but these are convex neighborhoods of some subset topology S. So actually this is okay. So all we have to do, essentially, is take one curve and contract it enough so that it is in the same neighborhood. So, so select R greater than 0, actually in 0, 1, 0 excluded, 1 included, sufficiently small, and we can actually say, since C2 is a relative open set, select R sufficiently small such that we have x plus sigma minus x times R as being subset to C2. And we'll call it sigma sub R. So now we have sigma sub R and gamma subset. Actually, we can just say, since p sub 1 of sigma sub R still has turning number 1 about p1 of x, then sigma sub R and gamma are freely homotopic in C2 puncture through x. So as we contract, since C1 is convex, sigma and sigma R are freely homotopic in C1 puncture through x, and thus in S puncture through x. And since these still have turning number 1, then sigma R gamma are freely homotopic in C2 puncture through x, and thus S puncture through x. So sigma, actually we can just say by transitivity of homotopy, sigma and gamma are homotopic in S puncture through x. So transitivity of homotopy is we just our first step is we start with sigma. Since C2 is a relative open set, we can select a sufficiently small r so that this sigma sub r curve, this sigma curve, contracted in the direction of x by a factor of r. We can select that r small enough so that this is a subset of C2. since C1, which sigma is a subset of, since C1 is convex, then sigma and sigma sub r, this contraction, are homotopic in C1 punctured through x. That's this lemma. Also, since we have, since C1 is a subset of S, then this is also homotopic in S punctured through X. Since the projection P1 of sigma sub R, it still has turning number 1 about P1 of X. So sigma R and gamma are also freely homotopic in C2. So both of these are curves in C2. They're both loops in C2 with turning number 1 about P1X, and C2 is convex. So by this result, they're now sigma sub R and gamma are freely homotopic in C2 punctured through X. But again, C2 is a subset of S, so they're freely homotopic in S punctured through X. And by transitivity, so if we first go from sigma to sigma sub R and then to gamma, these will be homotopic in S punctured through X. And that is it. The only thing I want to do is move all of these proofs somewhere else. So that's nice. Okay. Okay. Let's move all of these down. I have no idea what my appendices are doing. Okay, I'm gonna leave that and probably come back to it. Okay, so we're down here. So we had identity theorem. Some pontification. Okay, proper domain where for each x and s there is convex neighborhood and contour sigma such that projection P1 sigma has turn number 1 about P1x in the complex plane. This implies that S is locally convex and has no isolated points. Actually we can say, okay, yeah. If S is a proper domain for each point x in S, we let this circle x to S be the homotopy class of all contours which are freely homotopic over sigma, freely homotopic to sigma over this. This should be actually, let's do, give it some S subset to, let's put that up here. Okay, so a connected set is said to be a proper domain when for each x and s there is a convex neighborhood C and contour C subset to C as sigma subset to C punctured through X, such that the projection P1 sigma has turning number 1 about P1x in the complex plane. Notice that this implies S is locally convex and has no isolated points. If S is a proper domain, then for each point X in S, we let this set be the homotopy class of all contours which is freely homotopic to sigma over, this should be S punctured through X. This class is well defined, since any contour sigma 1, sigma 2, satisfying the proper domain condition for Sx are freely homotopic. Actually, we can say well defined since for any x in S and convex neighborhoods C1, C2, subset to S, and contours C1 subset to C1, let's just call this sigma gamma. Both satisfying the proper domain condition are freely homotopic in S punctured through X. Okay, so we're saying yes. So we're saying if S is a proper domain, we define this homotopy class to be the homotopy class of all contours which are freely homotopic to some sigma over S punctured through S, through S punctured through X. This class is well defined since for any X, and actually we can say since for any convex neighborhoods C1, C2, and contours, we can say loops. Any convex neighborhoods C1, C2, and loops sigma and gamma satisfying the proper domain condition are freely homotopic in S punctured through S. S punctured through X. This is proven in Appendix C, which it is. It is proven in Appendix C now. Okay, this is great. Okay, this is nice. Okay, so now we want to say okay, so for proper domain S and differentiable function f mapping the punctured domain to A, take any contour sigma in this homotopy class of S punctured through X to define the loop integral of f about X using this definition. This is well defined since f is differentiable and S punctured through X is locally convex, so the integral of f over homotopic loops is identical. We can also add this to the appendix. Maybe. Actually, you don't really need to. It's probably fine. And we actually don't need to extend this using the base point change because we've already done that. Okay, great. So this is very nice. Let's add though. So that's almost all of our assumptions that we've covered. The only thing we don't have is this length of sigma sub r is r times length of sigma. Let's put that in the appendix really quickly. Let's see, where do I? Okay, yeah. So down all the way at the bottom. we have this one. So let's actually say for any r in, actually, we can say for any r greater than 0, for any real r greater than 0, the curve r sigma, actually, actually, this isn't even worth doing. Oh, we can get rid of this now, because this is done. Okay, cool. Okay. I think we're actually fine. I think this is all fine. This one is not too hard to prove. Actually, it pretty much follows from the fact if you just differentiate, if you just take the derivative of this curve, the x goes away, this x goes away, and you just get r times sigma, which is actually r times sigma prime when you take the derivative. And it's really easy to prove the length function is linear. If you linear with not sums, but products by scalars, by real or complex scalars even. So actually this is fine. Okay, so this is nice. So we have this, and actually, I think this right away is enough. This right away is enough to prove our theorem. Okay, so our sort of ultimate result of all of this that S subset to A, B, actually let's just say that F map S to A, B differentiable over the proper domain S then F is analytic, and for each x in S, you can recover okay, and the Taylor series is supposed to be f of x is this sum n equals 0 to infinity, and let's see, it's written down x minus x 0 power n 1 over I2 pi times this integral x 0 f of z times z minus x 0 power minus a minus 1 dz. I think that is all correct. Okay, so our big claim of the analyticity section is, actually, this should be a circular integral. So our big claim is that if we have a differentiable function over a proper domain, then actually the function f is an analytic function. It's infinitely differentiable and equal to its Taylor series convergent in a neighborhood. And its Taylor series is given by this expression. So that's exciting. This is especially exciting because proper domain, the idea of a proper domain is actually pretty lenient. It's just a locally convex connected set. Actually, technically, it doesn't even need to be connected. But it's just a locally convex connected set with some convex neighborhood having these contours. So there's some there's at least one of the locally convex neighborhoods. At least one of those convex neighborhoods has this contour, which sort of encircles the point x, which is really exciting. That's very broad. So to prove this, it's really similar to the same theorem in complex analysis. So first we want to do, so we want to say, if we wanted to, we could also do continuously differentiable. That might make it easier. But essentially we're just going to say, let's think here. So find some contour sigma in this class actually we could maybe be a bit more specific. So we want to say let's find a okay, actually, I guess we'll start with this. We'll start by proving convergence of this expression, because it does converge. Okay, since f is continuous, actually we'll pick a contour. So we'll say pick any loop sigma in this class x0 set s, any loop through this punctured set going around x0, and we'll say, notice that since f is continuous on sigma, then it must be bounded. So we'll say let be in a real be such be a bound for absolute value of f. Then for each n, we have, actually we can also say, yeah, okay. Yeah, okay. So we'll say, actually we'll do something a little better. We'll say any loop blah blah f's condition sigma must be bounded. And we'll say similarly, since 1 over z minus x0 is continuous on a star, actually let me just say s punctured through x0. Okay, yeah. It must also be bound on sigma. So let C in a real bound C minus x0 inverse over sigma. Now for each n and n0 we have, so first things first, we want to bound the geometric term. So we have, actually, yeah, okay, so if we take the absolute value of the integral about x0, f of z, z minus x0, power minus n minus 1. So we want to bound that, and we'll do that by saying a of z minus x0, if we take this on the inside, p to the power of n minus n minus 1, by submultiplicativity, we have this is bounded by a z minus x0, power minus n minus 1, which is now bounded by our value c, power minus n minus 1. Okay, yes. And that means that we have a f of z, z minus x0, power minus n minus 1. This is bounded by b times c, power minus n minus 1. And thus we have this integral is bounded by the length of sigma times bc power minus n minus 1. Okay, nice. Let's line all these up. So we'll put a line there, and we'll put a line there. Okay. And actually this is easy. So now we've basically got it. So since we have capital Phi of our sequence, we have c power minus n minus 1. This is just the absolute value of p1 of c and this is also absolute value of p1 of c. This is going to be less than sorry, this is going to be greater than 0, rather. Actually, this should not be p1 of c. This should be the inverse of p1 of c. Also, we can say, we'll have to say, actually, no, this is fine. C bounds this thing. So C actually has to have P1 of C be greater than 0. This is this, which is greater than 0. Our power series has a radius of a convergence at least as large as actually just that. So since we have this phi value, we just have this exponential. This is going to be this P1 of C inverse. This is positive. Our power series has a positive radius of convergence, and thus converges in a neighborhood of x0. For all x in some neighborhood of x0. So we have convergence in a neighborhood first. So now we have to prove what it converges to. Give me just a second. Okay, so now we just have to prove that it converges to the function. So in order to do that, we will say, let's see, I think what we want to do, we want to swap this sum with this integral. That's actually what we want to do. So we can say, so this convergence is also absolute. That's going to allow us to permute the sum with the integral. That's what we want to say. So we'll say this infinite sum, so we'll have sum n equals 0 to infinity of x minus x0 power n 1 over I2 pi integral, actually we'll just do integral around sigma f of z minus x0 minus 1 minus 1 dz. So this whole thing is actually, we're going to permute this sum along with these x's and pull this right in to there. I'm also going to pull this f of z out of this summation. And now we just have a geometric series, actually. So we're gonna leave one of these powers on the outside. Now this should be inversed. So this is just a geometric series, which we've already investigated. So this is x minus x0. We can do a fraction. X minus x0 divided by z minus x0 to the power of n. This summation, actually you can put this up in the top part if we would like. Okay, this infinite summation, this is just going to end up being 1 over 1 minus whatever we have here. Okay, nice. So that'll be that. And then we can simplify this. So this whole thing, we multiply the top and bottom by z minus x0. We get this and that. And this fraction will just turn into this. We have z minus x0 inverse here, which cancels out with this numerator. And then we have z minus x0 minus x plus x0 x0's cancel out, and we just have z minus x. And that's it. So long as we have x on this interior. So we can say so long as we have sigma in s xs, then the theorem is proven. The problem now is we actually have to prove that there will be a neighborhood of x such that there will be a neighborhood about x0. So if we have a given contour sigma, that there will actually be a neighborhood about the point x0. There will be a neighborhood about the point x0 such that this power series applies. Oh, actually, that's trivial. Okay. Okay, I got it. Okay, so we're gonna have to induce a specific convex neighborhood. Okay, so take a loop, blah blah blah. Okay, so first we prove convergence, our expression. Okay. So take a loop sigma in here, Actually, let's say find and convex neighborhood X in C subset S with subset sigma subset to C. Leave the rest of this the same. We're just going to place S into a complex neighborhood. Okay, so find a loop sigma in this class in complex neighborhood, so that sigma encompasses X in X0 in this complex neighborhood C. And then we're going to say, since F is continuous on sigma, it has to be bounded. Let B bound the absolute value of F. Also, 1 over Z minus X0 is continuous on S punctured through X0, so it must also be bounded. So let C bound that. And then we just bound the integral using the length calculation. So the absolute value of these powers is the power of the absolute value, or bounded by the power of the absolute value, which is bounded by C to this power. Actually, let's do that a little better. This should be that's an error. That's fine. Okay, since we have phi of n plus 1, which is in P1 of C, which is strictly greater than 0, yes. Okay. Then our series has a positive radius of convergence, and thus converges for all x in some neighborhood of x0. Now we just need to prove that it converges to the function. Notice that the convergence is absolute, which allows us to permute the sum with the integral. So actually we can say let's do some more specification on this bound C. Okay. Okay. Since we have this thing, power series raised convergence positive, now you prove that it converges, blah blah blah. So then we can say, okay, so we can say, so long as we have the sigma in this class, then the theorem is proven. This will be true for all x in C, which have p sub 1 of x minus x0 as being strictly less than, actually the absolute value, as being strictly less than the absolute value of p sub 1 of, actually we can say strictly less than the absolute value of p sub 1 of sigma minus x0, say sigma t, for all t. So then we can say okay, I think that's it. So all we've done now, so we verified convergence first, as always. So what we're saying is we're saying we're saying oh gosh, words. Okay, so we put our sigma curve inside our convex neighborhood with sigma subset to C. So we're actually picking, so we're not just taking any loop in this set to do this loop integral on. We're specifically finding one which is in a convex neighborhood of this x0. So we start out by having sigma as a loop around the x0 punctured neighborhood. We end up with it having also being a loop around the x punctured neighborhood. Since f is continuous, it's bounded. Since the reciprocal function is continuous, it's bounded, because we're excluding 0, or the non-unit points. So this converges so long as right, this converges in a neighborhood. It has a positive radius of convergence, so it converges in for all x in some neighborhood. Now we just need to prove it converges to the function, and to do that, we notice, well, this convergence is absolute, so we can permute the sum with the integral. So this original summation, this whole expression, we're trying to prove that equals f of x. If we just permute the sum with the integral and rearrange some terms, this gives us, we have our f of z, we have our 1 extra power of z minus x0, that's right here. And then we have these n powers of x minus x0 and the other n powers, that's these, of z minus x0. This is a geometric series. This reduces to 1 over 1 minus whatever we're doing the powers of, which is this. Then with some simple algebra, this just simplifies straight down to 1 over z minus x. Actually, the x0 totally goes away. But we're still integrating on this contour sigma. This expression is roughly identical to the previous theorem. So we have this 1 over I2 pi of this loop integral around x of f of z over z minus x dz. Here we have the same integral, integrand, f of z over, I can make that more explicit, f of z over z minus x dz. Same integrand, same 1 over I2 pi, but we're integrating over sigma, this curve sigma, and that we don't necessarily know whether or not that's in this set. But if we restrict x in the convex set C, which is a neighborhood, and we restrict it so to have this sort of distance relation, so the distance between x and x0 on the first projection is strictly less than the distance between sigma and x0 for any t of the sigma, for sigma t. So long as we have this inequality, which will be satisfied because sigma is continuous and positive. So this quantity, this quantity will be bounded below by something positive. So we will also have sigma in this set, in this homotopy class for x instead of x0. Since sigma is in this homotopy class, this becomes a loop integral, and this is just f of x, and that's the conclusion. We can add a corollary. So our corollary will be this. So we will say f mapping S to A, B, on differentiable on the proper domain S. Then we can say the radius of convergence for this power series is at least and we can say supremum of the infimum of the absolute difference. So we'll do a supremum over all of the curves, sigma in these classes centered at x0. So the supremum across all these curves of the infimum of its distance, the absolute distance p1 sigma t minus x0. Okay. So our corollary is let's think about this. F, be analytic on I don't like how this is worded. Okay, there we go. So the proof for this is essentially the proof of this is essentially essentially just selecting this bound C here. So C just has to bound z minus x0 inverse, right? Okay, nice. Yes. So essentially, the corollary is essentially it's just observing that this has to converge on sort of the power series has to converge on sort of the largest possible radius. That we can't have a analytic function on a pretty large, too large of a domain, unless its power series also converges on that domain. So if we have our analytic function and our curve sigma in this homotopy group, so this curve going around x0, if we have some real number r strictly less than this absolute value, this absolute difference between sigma and x0 on the first index, the Taylor series of f at x0 converges with a radius of at least r. In fact, it converges with a radius at least as big as the lower bound of this. And the way to do that is, when we proved convergence, we just used this C bound, and we found that this power series converges with a bound at least as with a radius of convergence at least as big as the absolute value of P1 of C. But C was selected to be the an upper bound on the absolute value of z minus x0, but the upper bound on the inverse of that. The upper bound on this inverse is just the lower bound on the value itself on x minus x0, which is just z minus x0. And if z is in sigma, then we can just say we can select by selecting C to be exactly this infimum. Then actually P1 of C is just exactly the supremum. P1 of C is exactly this infimum, the infimum of the absolute value of P1 of sigma t minus x0. And since P1 of C is this infimum, and this infimum is greater than R, then P1 of C is greater than R. And our series converges with a radius at least P1C, so it converges with a radius at least R. And that's it. So that's a nice corollary. We can also, if you would like, we could also add let's see. I want to do an equivalence theorem. So we have a whole bunch of things now that are equivalent, actually. So okay, so Okay, so we're going to have some items that are equivalent. So the first item is f is analytic and f is differentiable. So we already have that by the previous theorem. We also want a few more. F has an antiderivative. Its antiderivative will be differentiable, and that's analytic. So f will be analytic. We can also say f has a path-independent integral. Or rather, that's not actually not correct. Not correct. Not a path-independent integral. We can say, actually that would be true if this was simply connected. Okay. Okay. Has an antiderivative, has a path-independent integral. And let's see, what else do we have? So we have analytic, differentiable, antiderivative, path-independent integral. And also there's what else do we want? Actually, we probably don't even need to do simply connected. We could probably do if we just did just as a proper domain. Instead of saying path-independent integral, we could say the integral of f on any loop homotopic to a point is 0. I think that would probably be enough. That would be enough to give it a local antiderivative, actually, or rather, a local indefinite integral function. Also, let me think, which one of these are weaker, antiderivative or indefinite integral function? I think having an antiderivative is stronger. Yeah. The condition for indefinite integral function being an antiderivative requires local convexity. And it requires f to be continuous. Actually. So this condition for an indefinite integral being an antiderivative is an indefinite integral is the weaker condition, I think, because we have f is, nope, not that one. Not that one. This one says every antiderivative is an indefinite integral function, acts as an indefinite integral function over the curves where f is integrable over. So having an antiderivative immediately gives an indefinite integral so long as it's integrable. Having an antiderivative. And we already have this condition. If we have an antiderivative, then we get this indefinite integral over when it is integrable. So the weaker condition to that would be we could say f has a local indefinite integral near any point. Let's see. I guess I can't really think of any others. I will leave that, I think, how it is for now. Okay, well, we can get started on this at least. So the equivalence of 1 and 2 the equivalence of 1 and 2 is an immediate consequence of our theorem, and the differentiability of analytic functions. That 1 implies 3. Actually, you can say locally path independent integral. So what's our theorems on this? Hold on. Not this. So that is, what do we glimpse agree? Locally convex, differentiable, blah, blah, blah. Not this one. 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 X without isolated points, which it is. Continuous. Every indefinite integral for f is an antiderivative. Okay, so that's if it's continuous. Actually, hold on, maybe it was this other one. Yeah, locally convex without isolated points. Indifferent integral function is an antiderivative. But it does have to be continuous. Okay. I think this is good. So, okay, so f is analytic, f as differentiable, has an antiderivative, is continuous, and is integral over loops. Homotopically to a point, vanish. Implies both 3 and 4 values on the integration. So 4 will imply let's read that theorem again. Okay, so if we have locally convex, which it is, without isolated points, which it is, every indefinite integral function is an antiderivative because it's continuous. Okay, this is nice. Okay, so what we've shown, so from our theorem, if we have a proper domain and a function f over a proper domain, then all of these conditions are equivalent. So f is analytic, f is differentiable, f has an antiderivative, or f is continuous and its integral vanishes over loops which are homotopic to a point. So we have analyticity implies differentiability, and differentiability implies analyticity. So the 1 implying 2 is really easy. We have differentiability of analytic functions. 2 implying 1 is from the theorem that we had just proven. 2 implying, so differentiability implying that we have an antiderivative and vanishes over loops which are homotopic to a point. That follows from our theorems on integration and differentiability. 1 and 2 are equivalent. 2 implies 3 and 4. Also, 3 implies 1. So if we have an antiderivative, the antiderivative will be differentiable, and that's analytic. So the derivative will be analytic as well. So 3 implies 1. So 1, 2, and 3 are equivalent and imply 4. And lastly, since convex sets are simply connected, the condition 4 implies that the restriction of f to one of the convex neighborhoods of S has a path-independent integral, since convex sets are simply connected. So all of the loops will be homotopic to a point. Since it has a path-independent integral, we can construct a local indefinite integral function, which will also be an antiderivative, since f is continuous, making f analytic. And thus, since this was it's analytic in this neighborhood of any point, it's analytic. And that implies 1. And that's it. So that's kind of nice. So all of these conditions end up being equivalent in a proper domain. And remember, a proper domain is just a locally convex set such that any point can be sort of surrounded by a loop on the first projection, a loop in one of its convex neighborhoods. And that's it. So that's actually a lot. That's a lot. So all of these sets are analytic. They're all differentiable. All these functions which are differentiable, analytic, have an antiderivative, or which have path-independent integrals. Actually, this is weaker than a path-independent integral. It's only saying integral vanishes over loops which are homotopic to a point, which is a little weaker than having a path-independent integral. You could probably add that if we wanted. actually, let me say f is continuous and has a path independent integral. Okay, so 1 and 2, immediate constants of a theorem, differentiable analytic functions. 2 implies both 3 and 4. Follows from our theorems of integration. We have 3 implying 1, so the integer will be differentiable. That's analytic. We also have 4 implying 3. So 1 integer equivalent. 2 implies 3 and 4. If it's differentiable, derivative, and path independent integral. I think it has to be simply connected. For antiderivative to be guaranteed. Okay, let's see that. Okay, that's nice. So yes, so I think that's maybe all we'll do for now. We could do a little more, but we've gotten through a nice amount. Yes. So the equivalence of all these properties is pretty neat, I think. We could also try, so I can check. We don't have very many other theorems to sort of pour it through. Mostly just theorems about oh, we could do this one. Yeah, okay, I think maybe we could do this one. So this one is yes, yeah, complex analysis is, it can get a lot. Yeah, okay, I think we can try this one. So we can try to say we can do this. So we can say so let f sub n indexed by n in natural. Let's have f and f sub n mapping s to a be differentiable on a proper domain, and have f sub n going to f converging compactly. Then, actually, sorry, put the cart before the horse. F is differentiable. That's in the proof section. That should be the theorem statement. Okay, so this one is okay. So actually, so this one actually follows pretty quickly from our corollary. So f is continuous and has a path-independent interval. So we can say okay, so we can say let sigma subset of S be a vector loop. Actually, we can say we want to take the convex case first. So we'll first say take the case where S is convex. Let sigma subset S be a contour loop, so that the integral on sigma f sub n of x dx is 0 for every n, since f sub n is differentiable and S is simply connected. So we're taking the case S is convex. We're taking any loop in S, any contour loop, so that this this integral is now 0, since each f sub n is differentiable. So remember, differentiable functions on simply connected sets have their integrals on loops vanish. That's number 4. So then we can say since each f sub n are continuous, actually we can say since the f sub n converge compactly, then on actually each, let's actually go like this. Okay, so since sigma is continuous, its image is compact, and since the f sub n converge compactly, then we must have f sub n, actually this is even stronger than We don't even need compact convergence. We just need them to be bounded. They just need to converge. They just need to be bounded and converging, isn't it? I think so, yeah. Okay, I'll let these be differentiable on a proper domain and have f sub n go to f. And pointwise, and oh no, maybe we do need compact convergence because we need them to be bounded on every compact set. That's fine. I'll just leave it like that. Blah blah blah. Image compact. So fn converge compactly. We have fn of x bounded for all n and x in sigma. Okay, so there we go. So we take the case where S is convex. Find any contour loop in S. The integrals of these f sub n's are 0, since each fn is differentiable and S is simply connected. Since sigma is continuous on the compact domain 0, 1, its image is compact. I made a typo here somewhere. There it is. Its image is compact, and since the f sub n are converging compactly, then we must have f sub n of x. They must be actually, maybe it has to be continuous. No, this is fine. Since the f sub n converge compactly, then we must have compactly. They must converge uniformly on the image over sigma. So f is continuous on sigma. Further, we must have the f sub n bounded for all x and n, since they are converging uniformly, and f is bounded. Yes, okay. So we have uniform convergence on sigma. The f sub n are continuous. We have the f sub n are continuous, converge uniformly over sigma. So f is continuous. This implies that f is bounded on sigma, and from uniform convergence, we also have f sub n bounded for all n and x in this in the image of sigma. So it follows from dominant convergence that this 0 is this, which is this limit of these. Actually, we could say, yeah, we can rearrange this. We can say this integral is this limit, which is 0. So the integral of f is the limit of the integrals of f sub n, and each one of those is just 0, so it's 0. And so we can say, and sigma was an arbitrary loop over S, it follows that f is differentiable. And then we can say in the general case that S is not convex, F is, since S is locally convex, since S is locally convex, then F is differentiable, and F is differentiable in each convex neighborhood, then F is differentiable everywhere, and that is the proof. Yeah, so essentially we just use this fact of if we have a compact convergence, whatever we're limiting to has to be continuous, and since we have it being continuous, then it's bounded, and we can then apply dominated convergence theorem on all these loops, just like that. So that's a nice one. Let's see, what else can we do? Okay, I think in my previous draft, the next proof that I have is extending complex analytic functions into real analytic functions into this into the context of A. We can do that one, or we could stop right now and do it tomorrow. Actually, I will leave it up to you, the viewers. Yeah, what do you think? Should we do that one now, or can we get back to it later? Or do you want to get back to it later? As sort of an indication of what that will look like, what we would end up proving is that if we have a complex analytic, so if we've got a complex analytic function, what we want to prove is that there is exactly one function which is analytic and extends. Yeah? No, really, I'm pretty sure you're the only one. YouTube gives you stream analytics, you know? And you're really the only person here. I'm pretty sure. Unless someone else is lurking and they don't show up in the analytics. But yeah, it's really just you. That's okay though, I don't mind. I'm having a lot of fun at least. Okay, yes, so yeah, we'll do one more. We'll do one more. Yeah. We will do one more. Okay, so let's see. I really don't like how these are spaced. I'll have to fix that later. I like how these ones are spaced. These ones are nice. But then this bit is just sort of cut off like this. Okay, so have a new theorem. And proof. Okay, so the theorem we want to prove is let F map. Actually, we'll say let O be a subset to C, and F map O to C the complex analytic. What conditions do we want to put in the set O? Be a actually, I think we just need it to be connected. f is complex analytic, then there's exactly one function, f mapping p1 inverse, the pre-projection of O, to A, such that f is analytic and the restriction to O is little f. Okay, I think that is what we want. So O is a connected set. Actually, we can just do, I don't know, S. I always do S for sets. Okay, so to prove this, we essentially want, so we're going to say, so we want to show that there is one, and we also then want to show that there is only one. So how will we do that? So we will say, let's do this in open, actually. We'll just do this open. That's fine. Okay. Let S be P1 inverse O. So S is the pre-projection of this complex open set. And so first we want to define our function. We define our function f as follows. And so we will say f of x is defined as equaling sum n equals 0 to infinity. It's just a Taylor series of, we have little f, nth derivative divided by n factorial, nth derivative at which point it will be taking the derivative at the p1 projection of x, and then we have x minus p1 of x power n. Right. Right, so we have essentially for each point x in S, we define this capital F function, f of x, capital F of x. Actually, maybe we should just use a different label. Okay, so we're going to use g instead. So we're going to define this function. G of x is defined as equaling this power series function. So for any point x, we just use the power series function for f, but at the projection p1 of x. So the first thing to know is that if x is in C, then p1 of x equals x. So for all x in O, trivially g of x equals f of x. So this happens in the case x is in a complex plane. P1 of x is x, so this is just 0. And all of these, this first term, when n is 0, the only time that this won't be 0 is when n is 0. And when n is 0, this is just f of x divided by 1. So, so it just reduces to that. From this, we do have the restriction, g restricted to O is just f. Now we have to prove that it's analytic. And actually proving that it's analytic is pretty much the whole theorem. So to prove that it's analytic, we have to show that each of these power series converge in a neighborhood to the function. So first we'll notice that they converge. So as for analyticity, at each point x, grades of convergence for the power series of f in, actually we can say by premise, it must be the case that the radius and coordinates of the Taylor series for f actually, let's do it this way. For each point, no, we'll do it this way, okay. Each point x in, actually do z in O. Consider this Taylor series. We'll call these capital F sub z of x defined as equaling all these summations. But instead we're going to use the center point z. Okay. Actually, let's do it x0 in S. And then instead of z, we'll do p1 of x0. Okay, so then we define a function g as g of x is just f sub x of x, and we'll do it like that. Okay. Positive rate of convergence. What do you want to say? So from this, we can find an open set B sub x0, which is just the open set, which is the set of x in A such that the absolute difference p sub 1 x minus x0 is less than the phi value of the coefficients, which are f nth derivative over n factorial nth derivative at the point p sub 1 of x0. Let's see what that looks like. Actually, I don't want to do this. Okay, so we defined at each point x0, we let this capital F sub x0 just be this power series for little f, but centered at the point x0. Then we define our function g to just be f sub x of x. So it's this power series centered at p1 of x itself. So same thing as before, just a little roundabout. So we have all the Taylor series have a positive radius of convergence. Since the radius of convergence C is the same as in A, for this we can find open sets, so open neighborhoods, x0 being in this B sub x0, which is subset A, on which f of x0 of x converges. So now we can say let's see. So you want to say that we want to say that this function converges to in a neighborhood to G. So what we actually want to say is that what we actually want to say is that every okay, yes, okay, since f sub x0 is analytic in b sub x0, we want to say, okay, we did this in an interesting way. Okay. Yes, I think, okay. So that's why it's a bit difficult. Is that we want these, we have to use the fact that the sets are vertical. That they are pre-projections. Okay. Okay. Okay, so we're going to do it this way. So we define our functions f. We know that the interior region of convergence for any power series is the pre-projection of some open disk. So we're going to let bx0 actually be the set of convergence, that set of convergence for the series of f sub x0. It follows that b sub x0 is connected and convex, and 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 b sub x0 is connected and con actually let me just say convex, is convex and contains both x 0 and p sub 1 of x 0. Okay, then we now define our function g mapping s to a using this following definition. So g for any x is defined as f of x, we're actually going to do it a little more general, f of x sub 0 such that x is in b sub x 0. Okay, so we're gonna define it generally as just this function. So g of x is f sub x 0 of x whenever it converges so that x is in b sub x 0. So firstly, to see that this function is well defined, suppose we had x sub 1, x sub 2, actually no, I want to do, let's do 0, 1. 0, 1 in S such that x is in both b sub x0 and b sub x1, which we'll label C. Then the set C is convex as the intersection of two convex sets. Thus it is, in addition to being convex, it is connected. And it must contain the point P1 of X. Actually, it's is open and convex. Open and convex at the intersection of two open convex sets. The set is connected, and it must contain the point P1 of X, which is in C. And we can say since the two functions f sub x0, f sub x1 are analytic and agree on the limit points, which is bx0 intersect bx1 intersects the complex plane. So since they are analytic and agree on the limit points in this thing, which contains the point P1 of X, since these functions are analytic, agree on these limit points, then they actually, by identity theorem, they must be identical. X0, x1, and S, such that X is in this intersection, which we'll call, that didn't get used at all. Okay, so this is well defined. So if you have two points, X is in this intersection of these neighborhoods. The intersection is open and convex, as the intersection of two open convex sets is thus connected, and it must contain the point P1C, since the two functions fx0, fx1 are analytic and agree on the limit points, which has this P1 of X. Agree on the open set. We say non-empty open set. Actually, this is relatively open. So then by identity theorem, they have to be identical. Over this intersected domain. So that proves that our function g is well defined. So we're saying for any point x in S, pick any point x0 which has x in its B set of convergence. Then define g as this power series centered at x0 of x. This is well defined since if we have x0, x1 in S with x in both of these sets, blah, 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 the intersection is open and convex. This is connected. So it contains the point, and it must contain the point P1 of x in C, which is a limit point since this intersection is relatively open. So since actually we can say if we had interested in opening that is so that is connected. Okay. The set must contain a point P1 of x in C, which is a limit point. Since this set is relatively open, and as the power series, actually Taylor series, f x0 f x1. Okay, there we go. So we have the set must contain the point P1 of x, which is in the complex plane, and it must be a limit point, since if we intersect these two B sets with C, this is relatively open, and fx0, fx1 agree with the lowercase function f there, because they are the Taylor series. Since the two functions are analytic and agree on a limit point in a connected set, then by identity theorem, they must be identical over this connected set. And so G is well defined. And then we can finally say, notice that if we have x and c, then p1 of x equals x. So for all x in this O, we have g of x equals f x, sub x of x, which is f of x. So from this we have this restriction. Okay. Okay, so we'll say, we'll put the uniqueness at the top because that one's easy. So let S be this pre-projection, and then we'll say since O is connected, then S is connected. And then notice that the key uniqueness condition on G is immediate from identity theorem so long as existence is satisfied. Indeed, if we had G1, G2, mapping S to A being analytic and agreeing with F on O, given that O is an open set, O subset to C, the complex one is an open set, it must admit a limit point. So relatively open set, so it must contain a limit point over which G1 equals F equals G2. Okay, so the uniqueness condition on G is immediate from identity theorem so long as its existence is satisfied. If we have G1, G2 being analytic and agreeing with F on O, given that O subset to C is a relatively open set, it must admit a limit point over which G1 equals F equals, this should be G2. Then we say, for each point x0, consider this Taylor series, f sub x0 at x. We know that the interior region of convergence for any power series is the pre-projection of some open disk. Let B sub x0 be that open set of convergence for the series, for for the series f sub x0, which must be non-empty since the analyticity of f implies the series has a positive radius of convergence. Posit bx0 is convex and contains both x0 and p1 of x0. For any x in S, having x in b sub x0, define this function g mapping s to a as g of x defined as f sub x0 of x. So long as this function is well defined, it is clearly analytic since it is defined in terms of the Taylor series, which are differentiable in this analytic. And for any x in O, we have p1 of x equals s at x. So for all x in O, trivially, g of x is f sub x of x equals f of x. So from this we indeed have g restriction. G restriction to O is f. Lastly, contain the point okay, so to prove that G is well defined, x1, x0, x1 in S in this intersection is open and convex, so it's connected. It must contain this point p1 of x, which is a limit point, since these sets intersect with C is relatively open, and both f x0, fx1 agree with f there. Since the two functions fx0, fx1 are analytic and agree on a limit point in a connected set, then by identity theorem they must be identical over this connected set intersection. So we have f sub x0 of x equal f sub x1 of x, and G is well defined. Since G is analytic, so we have G mapping S to A, which is analytic, and has G restriction to O equaling F, and is unique. Which is the claim. And that is it. Yeah, so that's it. So if we have any complex analytic function defined on an open set, there's a unique analytic extension to its pre-projection on this the first index pre-projection. There's a unique extension, which is analytic. There's a single function, which that's it, which is analytic. And and it always exists. That's pretty nice. Yeah. So all sorts of functions can be extended this way. Pick your favorite, really. Complex exponential, the logarithm with branch cut, different powers, raising something to the power of something else. We could do, I'll do a little bit more. I'll do one more, because it's short. But I'm getting pretty tired, so it will just be one more. Logging it. Hey, it's just a function like anything else. If you just ignore the multi-valuedness, it's just like a set of things. Just define it as, just pick a domain. You just sort of get your complex plane out, and then you draw your branch cut like that. And then, hey, this is a simply connected domain. Now you just have this whole simply connected domain. There's no holes. Since it's simply connected, if you just take the function 1/z, you can find its antiderivative there, and that's it. You just do that. Add the appropriate constant so that log of 1 is 0. Yeah, I don't know. Log is kind of fun. I kind of like log. It has some interesting properties. It has some interesting properties which still follow to this context, as a matter of fact, which is rather interesting. We could possibly do. It would not be impossible to import some of those rules. Yeah, yeah, you just sort of fix a point. I actually really don't like I don't know, a lot of stuff about log gets really confusing, because I think people don't want to like pick a function. They want to be like, oh, it's like all the functions, so we don't have to pick one. We can just be like, oh yes, it's multi-valued, and it's like, okay, but what if it wasn't multi-valued and we just picked one? And you can just pick one. They call that the principal branch. It's the one that you pick when you don't want to deal with the multi-valuedness. You lose a little bit. Like, for example, normally you want to say, I'm going on a tangent here, but normally you want to say something like log of z times s is equal to log of z plus the log of s. Normally you might want to say a claim like that, some kind of statement. Like that's a sort of standard log rule. That only sometimes works. Only sometimes. I think the contexts in which it works is whenever, I think it's so long as I think it's the imaginary part of s and z are both positive, it'll always work. There's a more complicated condition you can do where it always works. I think it's so long as, if you take the principal argument, so long as actually yes, so long as the imaginary part of the sum log of x log of z plus log of s, so long as this is actually in the range, what is it, minus I pi to I pi, depending on which branch you choose. If you choose the principal branch, it'll be that. But so long as this is actually in the image of the log function, then it's true. It just ends up being true. And you can guarantee that that happens when it's like the sum of the arguments are less than, you know, whatever. This is one of the conditions where that works, having both the imaginary parts greater than 0. That's one way to do it, because this guarantees that the arguments are both less than pi over 2, and so their sum cannot get up to pi. But you could do something like that. Yeah, it's interesting. It's strange, because you only get this equality mod I2 pi. You only get this equality mod I2 pi. But if you can guarantee that this right hand side is in the range that you don't need to subtract these I2 pi's, then you just don't have to have the mod part. So long as it's actually in there. You could do it another way. You could say, so long as the log of z plus the log of s is actually in the image, log of whatever your domain is. I always use capital S. In complex analysis, they use capital omega a lot. So long as it's in the image of the logarithm function, then it holds. Because if it's in the image of the logarithm function, you just don't need to do the modulo. Oh, yeah, it's the thing, because of I actually like this integral. It's kind of nice. So it's it just comes from the fact that when you go a full circle around, so if you define logarithm as the antiderivative of the reciprocal, you know, z function, you can try to think like you know, what are you well, it comes from this, really. That if you do a loop integral around 0 of 1 over z, positively oriented, this is just I2 pi. You can kind of work that out. For example, like you could say, let sigma be this map where you just map it to e to the I2 pi t. So if your sigma curve has this domain 0, 1, then t mapping to e to the I2 pi t, this just goes in a unit circle. Oh. Have you usually heard it like 2i pi or I pi 2 pi I? I think that's another one that people do a lot. I don't actually know how people normally do it. I've always done is I2 pi because I'm used to putting the I in front of the constants. Yeah. Yeah, I don't know. I just do it this way, I guess. It doesn't make sense. It doesn't feel right to separate the 2 from the pi. So, and if I put the I at the end, then I run the risk of accidentally doing, like if I'm doing LaTeX, it'll be /PII with no space, and it'll be, oh, I don't know what that is. And then it just goes away. Anyway, yeah. Yeah, logs are cool as long as, you know, it's good to just know what the domain is. Like what the domain and range are. I in front when typing it out. Yeah. Anyway, okay, we'll do one. So we'll say it's kind of a weird one. So Okay, so let's see. So we're going to extend the complex exponential to all of a, and we also let how do people usually notate the printable branch of logarithm? It's usually capital log. Capital letters, capital log. Let's see. Complex logarithm. Huh, I guess there isn't a convention, which is probably why I haven't figured it out, because it doesn't exist. Okay, this picture is using the branch that I'm used to, so I'm going to use that one also. Okay, so P1 inverse C set minus minus infinity to 0 inclusive. So the complex exponential, as well as sine and cosine to all of a. We also extend that principal complex logarithm, capital log, to the domain. It doesn't like that for some reason. Oh, it doesn't know what this capital log is. Wait, seriously? That's so weird. I don't like that. I'm gonna make it a command. Okay. I forget how to make commands. I have literally no idea what I'm doing. I'm just gonna shuffle around brackets until it magically works. Hey, it worked. Okay. Nice. Okay, okay, okay. Okay. Extend the complex exponential as well as the trigonometric functions sine cosine to all of a. We also extend the principal branch of logarithm, capital log, to the domain this, having log 1 equals 0, and branch cut along the non-positive reals. We further define exponents. Actually, we'll just say the square root function over the same domain using the square root of x defined as equaling exp of 1/2 log x. Okay, cool. Actually, we could probably just say x to the power of p is defined as just xp p log x. Actually, let me think about that. Principal branch of logarithm to this domain. Okay, nice. This is fine. Okay. Okay, so we've defined, extended the exponential function, sine and cosine, and the complex logarithm, as well as exponents. And now our example that we're going to do is this one. We'll say, for the next theorem, we extend the real and imaginary part operators to be pointwise, so that for any x, x in A and k in n, that's not right, and index k and n, we have the real part of x. If we take this projection piece of k, the real part of x is the real part of piece of k of x, and likewise the same exact thing for the imaginary part operator. Okay. Okay, our theorem is, if we take the exponent, hold on. Yes, the exponent of the real part of the log of x is equal to the square root of the real part of x squared plus the imaginary part of x squared. Okay. It doesn't like how I typed that. $16. Oh, that's why. Okay. Actually, we could probably even say, we could really go one step further. We could really say, no, this is fine. Okay, so for any x in this domain, this really does go further, actually. It's fine. Okay, we'll do x in this pre-projected domain. Where to go? Right there. So the pre-projection of the complex plane without the negative reals. So we have this identity. So you will probably recognize this from complex analysis. This is interesting though. So now, so our exponential is actually defined in terms of the Dirichlet series. So is our real part. It's pointwise. Our logarithm is defined in terms of Dirichlet power series. The real part again, the square root. This square is just the Dirichlet product square. So we have lots of interesting things. So the way that we work through this is we first note. So we note that the composition we have the composition exp of log of x equals x for any x in C, where defined. And since this should be capital L, since this function is actually, since these are analytic, it follows from identity theorem that this identity is true for any x in domain. So that's the first step. So the second step is we have next. So that's our first observation. So we have x is equal to exponential of the log of x. But this logarithm can be separated into real part and imaginary part. So that we could say this is the real part of the logarithm of x plus I times the imaginary part of the logarithm of x. Okay, just like that. So that's the first step. Now we can notice, so now, notice that the function, actually we can say, for each S, Z, and C, we have exp S plus C equaling exp S times exp Z. So we can say by leaving Z fixed, this is analytic in terms of S, so it must be true for all S in A. Then by leaving S in A fixed, this is analytic in terms of Z, so likewise it is true for all Z in A. So that lets us take this earlier portion. So we have this exponent of sums. That lets us break this apart. Exponential of this part times the exponential of this part, not plus. Just like that. Good so far. So the next thing we want to do is we can say, now that we have we have this portion, so we can actually apply Euler's formula. So from Euler's formula, we have exp of A plus, actually we can just say I times Z equals cosine Z plus I sine Z, or any Z in the real numbers if we want. But again, since these are analytic, follows from identity theorem that this applies for all Z in A. So we can break this down even further. Let's do that. Okay. So we have this second portion. Put this in parentheses. So we have this whole expression, the imaginary part, log of x. We have cosine of this plus I times the sine of this. Okay, now we want to do, we can actually do, I think we want to do a square. Oh yes, okay, I know what we want to do. Whoops. Okay, since the Taylor series for exponential at 0 has all real coefficients, and we have this expression here is in a sub-real part, so all of these projections are real, then also this exponential is in a sub-real, real on each projection. Okay, since the Taylor series for exponential has all real coefficients, and actually we'll note a subreal is a topologically closed subring, this real part is also real, then this is real. So then we have the real part of x is now proven to be this exponential times the cosine okay, and the imaginary part is proven to be the same exponential, but we're multiplying by sine instead. And this, by consequence, gives us real part of x squared plus imaginary part of x squared. This is just, we're going to have this exponential squared times, if we factor that out, cosine squared plus sine squared. Very interesting. Okay. Since we have cosine squared z plus sine squared z z equaling 1 for all z in real, since these are analytic, again, this applies for all z in a. So we have this is just that. Okay, wow. And then we can say, since we have the square root of x squared, or z squared, equaling z for all z and c with, I think we have the real part of z greater than 0. Isn't it? Let me think about that. Yes, okay. Okay, since we have the, this identity is true for all z in complex with real part of z greater than 0, and since we have this expression right here, we should have the real part of this on this first projection is should be greater than 0. You might have to verify that explicitly. Then we do get to apply the square root for the conclusion. So that gives us the square root of this left side is the square root of this right side. And that is it. Done. Very fun. Very nice. Yes. We could probably do with a little bit of justifying this. We could probably do that, but I think if e to the power of this real part of this logarithm, I think what we can say is, what we want to say is that this real part is always positive. But actually what we can do, we should have the real part of the first part of the exponential is actually the exponential of the first part. That should be the case. We'll have to justify that. But essentially this is the conclusion, which is very strange and unexpected. It's not what you would think. It's very original, because none of these, you know, operations mean what you think they mean, which I think is the fun part. Okay, that's the last one for today. I'm very tired, but I had a lot of fun, and we got a lot done also. We got quite a lot done. Okay, thank you for watching, if indeed you still are. I will be closing off the stream unless you have any other questions or things you want to ask about. Yeah, it was a good doing. Okay, bye. Thanks for coming.